Hi, my name is Paul Childress. I'm a postdoctoral research fellow at the Indiana University School of Medicine. In this video, I'm going to tell you about some of the work that I did for my doctoral thesis in the lab of Dr. Joe Bidwell, also at the Indiana University Medical Center. Dr. Bidwell's lab is primarily concerned with improving therapies for osteoporosis. Our experimental design was to overreactimize wild-type and Nmp4 knockout mice at 12 weeks of age and allow for 4 weeks of bone loss due to estrogen depletion. This mimics bone loss associated with postmenopausal osteoporosis in women. At 16 weeks of age, we initiated vehicle or intermittent PTH therapy to mice of both genotypes. The treatment periods were 4 and 8 weeks. Nmp4 knockout mice gained more trabecular bone than wild-type littermates at the distal femur. This is shown here in A, where the percent bone volume over tissue volume is plotted against various treatment groups. Representative micro-CT images are also shown in B. Similar to the femur, trabecular bone gain was enhanced in the fifth lumbar vertebrae of knockout mice at 8 weeks of treatment. This difference, however, was not statistically significant at 4 weeks of therapy. Again, this is shown graphically in A, with corresponding micro-CT images in B. Consistent with our past work in healthy mice, Nmp4 knockout mice have increased numbers of CD8 positive T cells in the bone marrow and in the circulating peripheral blood. Importantly, these differences are consistent across all treatment groups regardless of PTH therapy. CD8 positive T cells are an important positive regulator of the intermittent PTH response and potentially contribute to its enhanced response in the mutant animals. Also consistent with previous work in healthy mice, knockout mice harbor more mesenchymal stem and progenitor cells in the bone marrow at 20 weeks of age, though by 24 weeks of age, the difference between wild-type and mutant mice was not significant. However, by 24 weeks of age, the knockout mice did have significantly more of these cells in the peripheral blood. Again, these differences were regardless of PTH therapy, and we used CD146 positive and Nestin positive as our markers for mesenchymal stem and progenitor cells. In culture, the Nmp4 knockout mesenchymal stem and progenitor cells proliferate moderately faster as shown in A, and have a dramatic increase in mineralization when grown in osteogenic media. This is depicted in B. To uncover the mechanism for how this transcription factor restricts anabolic signals in bone, we conducted a genome-wide ChIP-seq assay in osteoblast-like cells. The resulting data was merged with similar data generated by the ENCODE consortium to identify a set of core genes in which Nmp4 binds to promoter regions in multiple cell types. Bioinformatic profiling of these genes indicated that Nmp4 was a negative regulator of biosynthetic processes, which corresponds with our in vivo observations in the knockout mice. Thanks for listening, and if you'd like more details on this work, you can see our recently published manuscript in Molecular Endocrinology entitled Genome-Wide Mapping and Interrogation of the Nmp4 Anti-Anabolic Axis. Thank you.